Okay, so we're going to get into chapter 5 talking about discrete random variables. And you could think of discrete numbers as what we consider like counting numbers. So humor me for a second and just in your head, count to the number 5. And I assume none of you guys went 1, 1.1, 1.2. You guys just went 1, 2, 3, 4, 5. So discrete numbers are just those counting numbers that we have. So if we're kind of doing a sample and we're trying to ask people questions, we're going to have, 20 people we asked or 21. We're never going to have like 20.4 or something. So discrete numbers are going to kind of be those whole numbers. And we're going to look at an example that we talked about in class about flipping a coin 3 times or flipping 3 coins. And you could either get heads or tails for each of these coins. Since we have 3 of them, we're going to be able to get heads, 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 tails, and so on. So right here, what we have is kind of the sample space that is listed here. And we want to be able to talk about also a random variable. And so a random variable just gives these outcomes a numerical value. And we're going to be a little bit more formal. We're going to actually denote this with capital letter X. So our random variable. And so really what this is doing is it's just keeping track of, it's assigning a numerical value and keeping track of whatever events we want. So for example, a sample space like this, I might be interested in the number of heads that I actually get here. So my random variable is going to keep track or keep count of the number of heads that we actually get. And so some possible, and so what we're going to also want to do is make a probability distribution function for this to just kind of help us keep track of this. And this is going to have our random variable X and then also the probability associated with it. So if we're trying to get or keep track of the number of heads, it's possible we could have 0, 1, 2, or 3. So for example, all tails would give us 0 heads. And that gives you a probability of 1/8 because it's just one of those out of the 8. If we want to look at for 1 head here, we're going to have these 3 here, where you could have heads, tails, tails, or tails, heads, tails, or tails, tails, heads. So it's going to be 3 out of 8. And we'll also look if we want to get 2 heads. Again, we're going to have 3 out of 8. And then all 3 heads is going to give us 1 out of 8. So a probability distribution function just assigns the random variables the probability, but it accounts for the entire sample space. And a couple of things with this probability distribution function is that the summation will always add up to 1. And those are some things we've talked about before. And then also each of the probabilities is always going to be between 0 and 1 because we're trying to make it a probability. And if you recall, we always divide by the sample space to give us that probability within there. And so this assigns the entire sample space multiple events that are disjoint, and collectively they end up giving us the entire sample space. So the probability will always give us that 1. One thing we're going to really be interested here is getting the expected value. So if I were to flip a coin 3 times, I'm really concerned about how many heads would I expect to get if that's what I'm keeping track of. That's really what I'm interested in. And so some notation here, that's capital E of X. And we're going to say this is a summation of X times probability of X. And we've done this kind of in chapter 1 and 2 with the frequency distribution table. So we're going to call this the mean. The expected value is going to be another word for the mean in this case. So if I want the expected value, what I'm going to do is this notation of X times P of X. Once we have our table set up, all we're really going to do is multiply these 2 values together, then multiply the next two, and the next, and the next. So that's what this portion here is telling us to multiply. X times P of X. Once we do that, then we're going to want to go ahead and sum all of those guys up together. So we're going to have 0 times 1/8. Then we're going to add that to 1 times 3/8, 2 times 3/8, and then also 3 times 1/8. And so technically this expected value is a summation of x of I times p of x of I. That's going to be our proper notation here. Oops, sorry, let me go back here. This is going to actually be our proper notation right in here. We're going to kind of not be so technical and ignore those subscripts here, as we have been before. And so once we add all of these, we're going to end up with 1.5. So if we were to flip a coin 3 times and we were keeping track of the heads, we would expect to get about 1.5 heads. Now, we can't actually get half a heads when we're talking about expected value and means. We're allowed to have decimals, even though originally our discrete values are not allowed to be whole numbers. But for means, this is going to be allowed. Okay, so let's look at an example here. And that's actually example 5.2 on the new numbering system. Okay, so let's read through this and then let's see what is the random variable. And so the random variable is what we're keeping track of here. And so x is going to equal the number of days she goes to class. And so here we're talking about Nancy. And what are the values that x could actually take on here? Well, she could go to class not at all if she wants to. So she could go 0, she could go once, she could go twice, or 3 times here. And then we want to make a probability distribution function here, or what we call a PDF table. And so for our PDF table, we want to go ahead and write down our x and then our p of x, the probabilities associated with it. So probability she goes 0 times is going to be 0.01. And this is coming from here, so no days. 1. Probability she goes 1 day, it's going to be 0.04. And then 2 days is 0.15, and then 3 days is going to be 0.80. So all of those values are given there. And then we want to know what is the expected number of days she would attend on any given week. So we have probabilities for each of them, but what would we expect? And so really what we're looking for is the mean in this case here. And so we're going to go ahead and use our notation here, our expected value. And it's going to be the summation of x times p of x. And so what I like to do is I like to extend my PDF table outwards. So we kind of already have a random variable with the probabilities there. And so I'm just going to multiply x times p of x here. And this is going to help us out. So we're just going to multiply across and write our answer there. And so here we're multiplying 0 times 0.01, which is going to be 0. 1 times 0.04, which is 0.04. 2 times 0.15, which is 0.30. And then 3 times 0.80, which is going to give us 2.4. And now I could go ahead and add these guys downwards. We're just going to go ahead and add those guys. But let's use our proper notation here. So that's a summation of x times p of x. And that's going to give us 2.74. So we would expect on any given week that Nancy would attend class about 2.74 days. Now again, it's not possible for her to attend 2.74. She would actually do 2, or she would attend 3, not actually 2.74. But when we're talking about a mean or expected value, we are going to be allowed to have those decimal values inserted there. Okay, let's try another problem with some expected values here. So let's suppose we're playing a game here with a biased coin, so not a fair coin here. And it's just a simple game, whether you get heads or tails, and we're either going to win or lose in this case here. So in order to get the expected values here, we're going to want to make a table. And so our outcomes here is that we win or we lose. And our random variable is what we're keeping track of. And we're keeping track of if we're going to win money or if we're going to lose it. So our random variable here is the money. So that's what we're actually interested in. So that's going to be our money here above x. And let's try to fill this in here. So if I win, we're going to go ahead and we're going to win $10. And if we lose, we're going to have to pay $6. So notice I made it negative. And the probability that we win in this case is going to be 1 out of 3. And then the probability that we lose is going to be 2 out of 3. And so again, you play each game by tossing the coin once. Probability of heads is going to be 2/3 here. And if you toss the heads, you pay $6. So that means this probability is associated with the -6. Okay, so let's find the expected value, which means I'm just going to multiply x times p of x here. And so 10 times 1/3, and then -6 times 2/3. And we're going to go ahead and add these downwards. So our expected value here is going to be the summation of this right here. And you can plug that in directly into your calculator. 10 times 1/3 minus 6 times 2/3. And it should spit it out for you. And you should get about -2/3, which is roughly about -$0.67, so about 67 cents. Now, a couple of things here. Notice I didn't really use the formulas. I don't want to get too heavy on that. I'm doing it a bit more intuitively, where I'm just multiplying these guys across to get my value, multiplying these guys across to get the value, and then I end up adding downwards. The negative indicates that we're actually going to end up losing money here. So on average, every time we play, we're going to lose about 67 cents here. Now, that's not going to happen on each play because we either win 10 or we lose 6. So the 67 is not going to happen, but this, we're talking about long term. If we were to play this game 100, 1,000 times over. So we're asking, would this be fair to play in this case here? And no, on average, long term, we would lose about 67 cents per game. Again, this won't happen on one single game. This is just going to be over a long period of time. This is what happens in Las Vegas on a roulette table. Long term, about 5 cents is lost per dollar bet. So imagine all the dollars being placed there over the course of 24 hours a day on all the roulette tables. On average, they only win about a nickel per every dollar that's played there. But it's happening all the time long terms. Now, sometimes they pay out, other times they collect, but long term it ends up averaging out to about that. Okay, let's look at one more example here. And we're going to call this example 5-4 just so the numbering system goes close. And I'm going to first do something that's slightly different. This is not exactly what this question is asking here. But let's first identify what is the random variable in this case. And once again, we're keeping track of money here. Now, if we win, we're going to win $256. And if we lose, we're going to end up having to pay $1. Okay. So that's our random variables we're keeping track of here. And if we're selecting a card here, what we're trying to do is we're trying to guess the suit of the card. And if you're not familiar with a deck of cards, there's 4 different suits. So it's going to be 1 out of 4 that we actually get it correct. And then 3 suits out of 4 that we don't. So our random variable here is money. So let's go ahead and find the expected value. And if we were just drawing one card here, our expected value here, we're going to multiply across. So that indicates multiplying this way. And then we're going to want to go ahead and add downwards. That way I don't rely on the formula. And so my expected value is about 63.25 in this case. So since it's positive, we would expect to win long term. On each game, we would win about $63 or so. So we would expect to win about $63.25 per game if we play this long term. Okay. But this is actually not what this question is asking here. This is for selecting one card. And that's kind of what we worked out right now. We selected only one card here. But this problem is actually asking us that we're going to select 4 cards in this case. So let's look at how that changes a little bit. We're going to go ahead and do the same table here. So win, lose, X, and P of X. But if we're going to go ahead and select 4 cards here, the probability to get the first suit correct is 1 out of 4. Then on the second card is 1 out of 4. Then again 1 out of 4. And then again 1 out of 4. That's our multiplication rule there in action, where we're doing multiple selections. So in order for me to get all 4 suits correctly, I'm going to multiply these guys together. And so if I multiply these guys, it gives me 1 out of 256. So that's a probability that I win, getting all 4 of them correct. That means I'm going to have 255 out of 256 that I don't end up getting it correct here. So we kind of did this with the birthday problem at the beginning of the semester, where a probability seemed unlikely, but then we added them up a bit. Likewise here, 1/4 seems pretty likely. It seems like a fairly good bet to win that much money, but we got to do it 4 times in a row. So we're going to do the expected value. And again, we're going to go ahead and just multiply across there. And we're going to do the same for the bottom. We're just going to multiply across there. And then we're going to want to go ahead and add them up for the expected value in this case. And our expected value is going to be 0.0039. So we would expect to win about 39 cents per game if we play this long term in this case. It's still positive, so we still end up coming out ahead, which is good, but it's a very, very small amount. Again, they're paying out $256, and then you only got to pay 1, but you have to get it 4 times in a row for that.